So now the final section of AP Calculus BC is on polar functions. Just like with vectors, this is going to be the calculus part is very similar to parametrics. And we'll get to that in a few videos here. I just wanted to take this opportunity to do some quick reviewing of polar functions since it's been a little bit over a year since you've done them. Just to kind of remind you here, what we're used to with x's and y's uh, are those are our rectangular coordinates. So for example here, these would be the coordinates of 4, 4. When we are working with polar coordinates, what we're looking at is the same point on the same coordinate plane. So you notice my axes are still x and y, but now to define how we get there, instead of saying go this far left or right and this far up and down, which is what rectangular does, we say I want you to go a certain distance r at a certain angle theta. And r is always the distance measured from the origin. Theta is always measured from the positive x-axis counterclockwise, like in the unit circle. So here, what we're talking about with this is I would need to know how long this piece is, which if my rectangular are 4 and 4, that's a 4 radical 2, Pythagorean theorem. And because it would make an isosceles triangle here, like this. This would be a 45-degree angle, but again, we always deal with radians, so this would be pi over 4. And so in polar coordinates, this would be 4 radical 2 pi over 4. And again, what this is telling me is a distance to go from the origin at this angle. And it gives me the exact same point, just a different way of how we get there. So kind of some quick reviewing here. If we have these points in rectangular coordinates, uh, how would we, or I'm sorry, these are in polar coordinates, thinking of them in rectangular. So 4, I'm just going to use colors here, 4 pi over 2 would be, pi over 2 is here, 4 units. Well, rectangular-wise, those are the coordinates 0, 4. Negative 3 pi, well, negative 3 means I'd move backwards. So if I go to pi, but then I go backwards 3 units, that would be at 3, 0. If I look at 16, 5 pi over 6, well, 5 pi over 6 is out here. And 16 would be saying that's how many units this is. Well, that's a 30, 60, 90 triangle. So this would be 8. This would be a negative 8 radical 3. So this would be negative 8 radical 3, 8. And then finally, negative radical 2, negative pi over 4. Well, negative pi over 4 means I'm moving clockwise, but negative radical 2 means I move the other direction. And if this is a length of radical 2, then this would be 1, and this would be negative 1. So this would be at negative 1, 1. We can also do some graphing of more function type rather than points. With the functions, it requires a little bit different way of thinking about these. Uh, just starting with some basic ones that are just in terms of r or theta. We'll deal later with what if it's both. So if r is 2, this is telling me that my distance from the origin is always going to be 2, no matter what the angle is. So, I could have it at an angle of 0, or an angle of pi over 2, or pi, or 3 pi over 2, or pi over 4, or 5 pi over 6. And if I just kept picking all these different angles with a radius of 2, what I eventually get is a circle. Similarly, if r is negative 2, again, this is telling me it doesn't matter what the angle is. No matter what, my radius will be a negative 2. So if I have a radius of 0, or angle is 0, that would be my radius of negative 2 at pi over 2, at pi, at 3 pi over 2. And again, going around to a whole bunch of different angles, it wouldn't matter. I would still get a circle. Now, if I'm being told that theta is pi over 6, this means that the distance from the origin, r, doesn't matter. It could be anything and everything. I just must have an angle of pi over 6. So if I look at this as here, I have an angle of pi over 6. Well, if r is any positive number, it's just going to keep going out on this line forever. And then if r is negative, it's just going to go the other direction forever. And what I actually get is a line. We are able to graph these on the calculator. If we look at our calculator does need to be changed into polar mode. So if we hit mode, polar is the third one down. And now when we hit the y equals button, we see that it's all in terms of r equals. And we do treat r as the dependent variable and theta as independent, even though I know in the way we write the ordered pairs, r comes first, which is a little bit different. So if r is sine of 6 theta, I do sine of 6, and then theta is also the x button here. I like to use zoom trig on this. It's not always great, but it tends to fit these windows well because of the angles we're using. That's a little bit small there, so I'm going to zoom in a bit just to help make it a little easier to see. And oh, I've got a 12 pointed rows. Uh, Similarly, if I go through and I look at 1 minus 2 cosine of theta, again, I'm just going to start with zoom trig to see how it looks. That's a pretty decent one. And what we have here is called a limison. And then finally, if I do r equals 4 sine of theta, and again, I'm just going to try a zoom trig to see if it's going to work well. And in this case, it does. So we get a circle in that case. If you're interested in kind of reviewing some of the names for some of the shapes that are made, like the rose and the limicon or the lemniscate, cardioids we don't really treat with because they are actually a special case of a lemniscate, or I'm sorry, of a limicon. But if you want to, you can look on page 562 to 563 in your book and has a little summary of all the different shapes.